All right, so this is example number 9 again. I've rewritten it slightly, just a little bit shorter, but the idea you should be able to get from the question in your note packet, you've got a big mass that's on top of a table. We're saying frictionless just to simplify things. You've got a small mass that's hanging off the edge. You've got a pulley. We're going to say ideal pulley, ideal string, which means they don't have mass. They're not going to affect the problem in any way. We can just leave them as is. And so essentially it should be pretty obvious that what's going to happen here is that this mass is going to fall down and the whole thing is going to kind of shift over in this direction. It's going to rotate in that direction. Okay, what I would like for us to do is we're going to find the acceleration of the small mass, and we're going to find the tension in the string, but we don't have any numbers, and so we're going to do everything in terms of the given variables and known constants. All right? So just so that we're clear, what are the given variables here? The big M and the small m. Okay? That is not a given, right? We're trying to solve for t. Otherwise, I'd just be like, oh yeah, t equals t, done. Okay, so gravity would be considered one of these known constants, right? So when we use that g, that 9.8, that is considered a known constant. So we're not going to put 9.8 into the question. We're going to just leave it as g. Okay? We may come up with some other things as we go, but as far as we're concerned at this point, those are the 3 variables that I'm allowed to have. Okay? Now what that means is that when I get my final answer, the final answer can only have these 3 things in it. It cannot have a t, it cannot have an a, it can't have any other, it can't have velocity or any of those other things. It can only have these 3 variables. All right? So, can you guys start me off? What might I do to start this? Okay, do a free body diagram. All right, let's start with a free body diagram. What do you want to do a free body diagram for, Dinesh? Okay, so Dinesh says, let's take the small m there. Let's do a free body diagram for the small m. So what are the forces on the small m? We got force of gravity down. So we'll label that as the force of gravity on that small m. And tension. And oh, and nothing. Oh yeah, you're right. Nothing else. I was just checking. All right, so you got tension up, force of gravity down. All right, we got a force free body diagram on M. Now what? Okay, so let's try the some of the forces equals MA. Awesome. So you guys are pretty familiar with this right now. So you just go, all right, I got the negative force of gravity on M. I've got the tension that's going up, and that should equal the mass, which is just the small m, that's right. And then that would be times the acceleration there. Awesome. Okay? Looks good. Then what? You want to do the same thing for the big M? Is that enough? I mean, does that answer either of the questions? Could I use that to answer either of the questions? What are you thinking? Okay, so could I use that then to calculate the acceleration of the... Owen says no.
You need to know what t is.
You find AM and T.
Yeah, but if you find what t is, then you can put that into that part.
The acceleration is
So some of you are starting to recognize, well, I could here, remember you have to only use these 3, right? So some of you are saying, well, yeah, this could be mg, right? But that's still going to be t, and this is going to be ma. So even if I divided everything by m, I still have t. This is example number 9 from the packet. So I still got t. T is not allowed. So even if I did that right now, I would solve for A, but it would not answer the question because the question has to be in terms of these variables. And so I'm starting to hear little bits and pieces of, oh, well, if we solve for T, we could put that in. That is the right direction that we want to go in. We could substitute for one or the other. All right, so what do you want to do? We'll find T. How are we going to do that? Just what?
Couldn't you do the same with the big M and the substitute?
Okay, let's see. Let's do a free body diagram for the big M. Some of you were talking about that before anyway. So let's go ahead and let's do the big M here. All right. So there we go. What are the forces on the big M? Okay, force of gravity, which is on the big M. What else? Oh, I heard somebody say tension. All right, tension is going over to the right. What else? Okay, normal force. What else? Friction. I think, does number 9 say frictionless? It does say frictionless, so no friction. That's what you get for walking in 40 minutes late. Just kidding. What else? We're on example number 9. What else? We're looking at the forces on M right now. So just forces on M. Anything else? Dinesh says no. Eamon says no. All right, I got another no. We're going with no unless somebody stops me. All right, very good. What would the equation look like then? Somebody said do the same thing, so I'm doing the same thing. What would the equation here look like? Okay, so we go sum of the forces equals MA, and if I look at just the horizontal forces, because that's the direction of the acceleration, then I would go T equals MA. Yeah, and I can do the same thing with the vertical, right? I could go Fn minus Fg capital M would equal Ma, but what's the vertical acceleration? 0. So that one would, the vertical, this would be vertical. This would be horizontal over here. And so we've got that. Does that help?
Yeah.
Why does that help, Shakla?
Can't you just put it into the equation here?
Okay. Sorry. We do need to be careful. What M is this? That's the big M, so make sure you put that in. Okay. We're treating T as positive, right? This is one of the things that you have to be really, really careful about if you're going to be doing substituting with things that are changing direction. Okay? And we have a workaround for this, but I need to mention this right now because we have to be really, really careful if we're going to take something that's horizontal and put it into something that's vertical, because the positives and negatives are challenging. They change, right? Your positive was up, now positive is to the right. Or your negative was down, now it's to the left. It's very, very different, because right here we've got tension, which will then give me a positive acceleration, right? So if I were to plug this in for T, this would assume that my acceleration is positive. Why is that a problem if I put it into my vertical? The acceleration there is negative, but I just assumed it was positive. It cannot be positive and negative at the same time. So how would I deal with that? Okay, one way would be, why didn't we just do a system in the first place? Owen says, that's what I was saying. All right, but what's the other way that I could deal with that? Because you can deal with it. Okay, we need to change one of them to be a minus. We do need to deal with that plus or minus. If I assume that acceleration is positive here, then here I need to show that it is negative. All right? And so I'm going to adjust that slightly to show that this is equal to negative MA. Okay? And the reason is, if I'm going to substitute in there, this assumes a positive acceleration. I need the acceleration here to be negative, therefore I'm going to show that it's negative. And that, in some ways, you can almost just set that up every time anyway, because the acceleration is downward. And so you could, just like we made the force of gravity downward with the negative, you could just put the negative there and say, I'm going to make sure that I get negative. Okay? Now what's going to happen is when I calculate A, I'm going to get a positive number. And so you're going to have to then, at the end, decide, okay, well, for this situation, acceleration should be downward, it should be negative. For this situation, it should be positive to the right. Okay? So, we could, as you guys suggested, we could take our tension and then substitute it in there, and then we'd have the MA. So let's go ahead and see what that looks like. So now I'm going to take this guy and put it in there. And so we have negative mg plus the tension, which is that capital MA, which is then equal to negative MA. Can I solve for the acceleration now? Yeah, how would I do that? Okay, I need all the A's on the other side, so I'm going to move the big MA over. So I'm going to go minus big MA, minus big MA. So I'm going to have negative mg is equal to negative small ma minus the big MA. Then, this is what you guys did in your summer work, right?
Factorize it.
Yep. Factor out the A. So I'm going to have negative mg is equal to negative m minus capital M times that A. And then divide by the negative m minus m. And I get negative mg over, sorry, I got to make sure that's a g, not an a, over negative m minus capital M equals a. And we now have an acceleration that is only in terms of the variables that we said were okay in the beginning. Jacob.
Could you put that into positives? Like, could you just put
Absolutely. And if you wanted to, you could say, well, a negative divided by a negative is going to be mg over m plus m. Absolutely. Which should then end up giving us a positive A, just like what we said it should be.
Would AP take points off if you don't do that?
Nope. Nope. AP is totally okay. As long as it is algebraically equivalent, then they're fine. The one thing that I would say to be careful of is that they don't like to have fractions inside of fractions. If you have a fraction inside of a fraction, they expect you to do a little bit of algebra so that it's not a fraction inside of a fraction anymore. That's the one thing that I've seen tends to, they're a little bit more picky about. Technically, they should still give you credit. But sometimes that's a little bit harder to work through and figure out, is this really exactly the same thing as what the answer key says? And so you're taking a chance. So I would say if it is fractions and fractions, work it out. Otherwise, yes, this is 100% okay. No problem. Everybody okay? The other part of the question was to get tension. How would I get tension?
Put a
What's there? From, okay, yep, I could move the mg over. Now that I have an A, I could plug that in for the A. Remember, A is not allowed. You can only use the variables that they allow. You could do that. Or we could step right back to this one as well, right? And you could just put that in for the A here. Because we know that the tension on this block has to be the same as the tension on the other block. But either one of those would be acceptable. Okay, you don't have to do all the simplification. The fact that you say, okay, in order to get the tension, I need to take my acceleration and put it back into one of those, That's enough. Okay. Y'all doing okay? Can we do it the easy way now? Go ahead. All right. Let's do it the easy way now. What's the easy way, Owen? Let's make it a system. All right, let's look at a system. So a system means we're going to take the whole thing. And I know, Jacob, when you looked at this question, the first thing you said was, it's a sock problem or something along those lines. Okay, so the system, the sock. Okay, we're going to look at what are the forces causing it to accelerate. And remember, clockwise is negative, counterclockwise is positive. So we can, again, use the free body diagrams if we want. We are going to, let's see. We're still going to do our sum of the forces equals MA for a system. All right. So we got sum of the forces equals MA. This is the system. So go ahead, help me out. What are the forces causing the system to accelerate? Shruti, what's one of them? Tension's inside. Good call. Yep, which one? Okay, force of gravity on M would cause acceleration, right? So we would go force of gravity on the small block. Okay, is that going to be positive or is that going to be negative?
Negative.
Why negative? Because it's going this way, right? Ignore everything else. Just look at that force. If you were just to pull on it in this direction, which is what gravity's doing, that would cause it to rotate clockwise. That would be negative. So we're going to go negative FGM. Sorry. Any other forces cause the acceleration? Jacob says no. Dinesh says yes. Oh, that's a yes that it's no. All right. Jacob won the Kahoot, so he must be right. All right, good call, good call. If you look at all the other forces, we've done the free body diagrams, right? These two, number one, they're the same. They're going to balance out. They're going to cancel. Number two, they're up and down here, which is not the direction of the acceleration. So those aren't important. Tension, as Shruti said, is internal. Therefore, we are only left with one force. You're not going to add in new forces that weren't existing before by creating a system. So if you've already done the free body diagrams, you should be able to just look at those and determine what forces are important. So that's the only one. Equals mass. Yep, because it's the mass of the whole system. Remember, we're talking about the whole system here. How much mass does the whole sock have? So it's going to be the mass, which is big M plus small m, and then acceleration. Okay? Force of gravity, of course, we know is just mg. Remember, that is the force of gravity on the small mass. So that's just going to be negative small mg is equal to capital M plus m. And then, of course, you just solve for a by dividing the m plus m, and we get negative mg over capital M plus m is our acceleration. Which is essentially what we came up with here, except we have a negative. Oh no, why do we have a negative? Yeah, remember in this question, we made the assumption that the acceleration was positive because it was going this way, and so that's correct. In this situation, the acceleration is going in what we've defined as our negative direction, so therefore we end up with a negative. Okay, and as long as we've defined it, we've clarified what positive and negative are, that's fine. All that matters is that. Of course, once we get that, then we go and we substitute it back into one of our accelerations to be able to get the tension. Cool? Questions?
So with the system thing, you consider the full, like the forces acting upon both.
Yep, because they're part of the system. And so when you treat the system, you look at all the forces acting on the system, but all we're interested in really are the forces that are causing the acceleration, right? And so when we look at this block, the only forces that will be important are the up and down forces, because that's the only way it can accelerate. When I look at this block, the only way it accelerates is horizontally, and so I'd only be worried about that. You can get questions that are on a slant, right? And on the slant, all that we care about is acceleration in this direction, right? And so when you look at it, yeah, really all we're interested in are the forces that are in that direction, or of course that have components in that direction. And those will be the things that we include when we do our system forces here. Anything that cancels out, anything that's perpendicular to the motion, none of that really is, anything that's internal, none of that matters. Any other questions? So I waited just long enough for that one question. That's a good question. Okay, awesome.